think about on a computer, etc. Okay, so that's next week. The week after that, you guys are going to be singing, right? Good. And then following 3 weeks after that are going to be, again, you guys are going to be singing up here, presentations. And that's pretty much the end of the show. Right? So I'll talk today, talk next week till we run out of things, and then you write and then you talk. Are there any questions about anything as far as the material, the presentations, or anything at this point? As you see, I've posted the schedule. Somebody asked me if it's possible to go another day. The only way it's possible if you find somebody else to switch our section with. Okay? As you see, it's divided into 10, 10, 9. I do not want to increase the number of presentations a day simply because we cannot run out of time. Okay, so I'm okay if you want, for whatever reason, go another day, as long as you find somebody else in the class who's willing to switch with you. Okay, other than that, good. Any other questions? No questions.
How many slides?
I'm okay, let's talk about that. It's not really the number of slides, right? It's not really the best measure. Time is given about 10 minutes, okay? Plus 1 or 2 questions, something like that. So I'm going like 15 minutes for a full round. So I usually, when I prepare slides for presentations, not lectures, but conference or something, I usually do a slide a minute on average. Some slides longer, some slides shorter. So if you have, say, you go for 10 minutes, 10 slides, not more. Less is okay if you talk more about the material that's on a slide. But, if you come with 25 slides, then probably not going to be good. So slide a minute, it's a fairly decent measure of how much can be presented. But again, font size and all that, I mean, you think of it that way. If you guys in the back can read this font type, and I think this was 28 or 32 or something like that. So if this is legible, then, don't make it too small. There's no point in cramming a lot of information onto a slide, so choose carefully. After all, your slide is your report. So it's part of the mark, what's on a slide and all that. You're presenting a technical topic.
So you have to submit a report with the presentation?
No, your presentation is your report. Pardon? Oh yes. References all go like any report in the back. So again, how many references did I say? Yeah. The key word is the at least. If I see 5 good journal articles, I'd say, okay, references done. Good. Passing the reference part. If there is 15, 20, then we're talking. So, okay, the student did the work, found all sorts of information, has a very good understanding of the issues as presented by all sorts of papers and everything. So, 15, 20 journal articles. Good. 5 is the minimum. Practice. Practice and practice. Right? That's the best way to sound confident about the topic. I mean, after all, the whole idea of these presentations is that you present a topic not covered by me in a course to the rest of you. Not really to me, but it's for the information of the whole class. So, do a good job, let everybody learn. So it's a very good exercise in public speaking, which I value a lot because any job these days has a huge component of explaining ideas to various audiences, be that your peers, your bosses, the general public, whatever. So, 30, 40, 50 years ago, engineers were pretty happy sitting in their little office or cubicle and calculating all day. No talking, no nothing, no report writing. Now, everybody talks, everybody writes, so why not? It's for your benefit, believe it or not. Why not practice it, public speaking here among your friends and colleagues than in front of a bunch of unknown people when you go to your job interview? So, practice. Any questions about the projects at this point?
So the time in 10 minutes is the minimum or the approximate?
Look at it this way.
How long is the derivation before the law?
Truncated normal distribution. What happens in 12? Yeah, I'll stop. Around 12, everybody's happy. If you come up, you say your name, you bow, and you go back to your seat, I'm not going to be particularly impressed.
Can we send, I don't know if you did this said before, but I realized they're late. Can we send the slides to you earlier? And maybe give a check. See if we
Upload, everybody has to upload it, as it says on the, I believe on the course outline or somewhere. On a 28, everybody, irrespective of when you're presenting, to be fair to everybody, it has to be uploaded on the 28 by whatever it is. I think I already created a place to upload it. So before that, you can come to my office hours. I can quickly take a look at it. If something major issues that I see, then I'll draw your attention. But as far as you and I are concerned, this is not an iterative process. Okay. So if you come, you show me the slides, I say, okay, they look good or too much, too little, to help the content. So, 12 minutes would be the maximum. For the simple reason is that, if these things start going, that somebody does 15 minutes, then the next one 17 or something like that, we're going to stay here till the next class comes in. Part of the exercise is to work in the allotted time. So it's 10 minutes, if it's 10 and a half, or 11, whatever. Or if it's 7 minutes and it's a good one, I'm good. It's the guideline. Any other questions with the time? But the essence is to give me a summary of your chosen topic. What it's about, why is it relevant to the course, what are the issues, what are the complications, how do we solve it if it's a practical problem, how do we solve it, the implications, few examples as far as case studies are concerned. There is no time to derive equations, there is no time to go through a long material and stuff like that. Okay. Whatever you do, don't play a video unless you're narrating it, because I can't really find everybody who created the video and gave them your mark. Because I want you to talk, not them. Okay? You good? Good. Excellent. Any questions about that? I'm really surprised that I don't see many of you in my office hours with questions related to this part of the course. So I'm guessing that if you don't come, that everything is good, everything is okay, and it doesn't need to be too much explanation. You're shaking your head. You know where my office is. Okay, because I can, easily ask you to derive any of these or add to it or explain certain things. So what I've been trying to say, and just for a moment review it, let's review the GLE. But even once you have the basic setup as far as quantities, from then onwards, it's pretty, as you see, pretty the same procedure. What is the strength of the material for that slice or along the failure surface? What are the assumptions as far as force equilibrium or moment equilibrium per slice? You set things up. Ultimately, you gather all the equations to satisfy whatever the method claims for equilibrium. Let's say this one, let's see what we have. We had sum of Fy equals 0 for the slice. That was one equation. Sum of x, or Fx rather, equals to 0 for the slice again. Moment equilibrium, is it for the slice or for the whole slope? Yeah, this is a summation, right? So this is for the whole slope. And so forth. So you fill in all the equations, and the method itself is the same. You state what assumptions you have. Remember, we talked about the three equations of equilibrium for a slice, three equations of equilibrium for the whole slope. So depending on the method, and there is this good summary set of slides later on that shows you what each method claims. So when you're deriving them or you're putting things together, then those are the quantities that you're addressing and explaining. So let's just go back to the GLE, generalized limit equilibrium. So this would be, depending on what I'm assuming for the interslice forces, I can derive many other methods that we covered so far based on it. So Bishop method, remember it says that the interslice shear forces are 0. So if I make that substitution into the equations here, I would be able to retrieve Bishop's method. Now, you have to keep in mind that Bishop's method only is derived for circular failure surfaces. So GLE is good, that it has the ability to have both circular and non-circular. And on the other hand, Spencer's method and the Morgenstern price I explained last week, that I can change the inclination of the failure surface and the interslice forces. So just to recap, I asked probably the very same question last time too. Which one would you pick for something like that or for something like this? How would the interslice forces be oriented? Which of these little figures would you pick for the orientation? So let's say for the top one, which one looks good? There's a question. I'm expecting an answer.
Left bottom.
Okay, so he says for the top one, a trapezoidal would be good. Anybody else?
I don't agree, but I don't know why.
You agree?
Like it looks edgy. That's what looks edgy. So yeah.
Okay. Anybody else agrees or disagrees? It looks similar, but both are slow. There's a subtle thing hidden here that you have to say for this one, pick one out of the four that's on there shown. Which one would you pick?
Yeah, bottom left.
So we have two for bottom left, and it's one who agrees with bottom left. Okay, you guys are right. I mean, think of it this way, that what it shows that there is an inclined portion at the two ends and it's pretty much horizontal in the middle. So I would have something like this, this, and maybe like that. Okay, so how about the bottom one? You would have to pick one of the four. You pick the same one, some different one. All right. So we have one going for this. Anybody else?
Bottom right.
That one.
Yes.
Okay, so bottom right and top right. Top right. Anybody else? So again, the moral of the story is that you have something that's coming sort of down, turns, and if I add another one, it comes up. So there's not too many horizontal ones, right? Horizontal components. Something like this, or if you go with the user-defined one, and let's say this was the midterm, then if you specify me a shape that not just a bunch of squiggly lines, but something that's appropriate to the problem, I would take that. So I would have picked this one, but if you pick that one and you made a case that what it should be like, then I would be okay with that one. Everybody gets the moral of the story?
How is that case going to be?
This one? Well, you have to make up something that looks like this. So this is like, pretty much you're digging your own grave if you don't get it right. But you open the door to it, so I'm okay with it. If you justify it that, well, not really this one, not that one, I want my own function, and this is what my function looks like. Which I might give you a problem like that, and you have to make up your own function and justify it. Nothing wrong with that, it's all good. Now, for GLE, the funny thing was, if you remember, that there were two equations for the factor of safety. One of them claimed, go back to this one, one of them claimed an overall moment equilibrium, right? Factor of safety equals whatever. And then another one claimed an overall force equilibrium. Right? So I have two factors of safety equations. So what is the factor of safety then? And that's what this little figure tells you. One equation of factor of safety, another equation of factor of safety as a function of the interslice force inclination. When they intersect, when Fm and Ft intersect, that is giving you then the factor of safety under a condition that both of those equations are satisfied. Everybody sees that? So that's how I would deal with two factors of safety equation, that when they intersect, i.e. at the volume of Fs, at that point is same for the both of them, then that is the factor of safety that satisfies both cases.
That's the minimum.
That is the factor of safety. You have to satisfy two equations simultaneously. So it is their intersection. If you go any further up, then they diverge. Right? They're not satisfying the same at the same time. Okay, so if you look at Fm, for the slope, the Fm, the moment one, never gets below 1, right? Ft is below 1 for up to whatever, 13 maybe, for the interslice inclination. So you have to satisfy both of them. And the only way to do it is to find their intersection when the factor of safety is 4. I mean, it makes sense. You have two equations or two constraints. You have to find a solution that satisfies both of them. Now let's look at another one. And as you see, with an escalating complexity, the non-circular methods can be set up such that they can use for circular cases. Whereas as we looked at, say, Bishop's method, that was circular only, you cannot do non-circular situations. So Jambu's method, and he has a few, so I picked the reverse method. It works for both circular, non-circular. However, there is a huge assumption about something called the line of trust of interslice forces. And what it means is, if we go back for a second for these, this tells me what is the variation for the inclination, right? This angle theta. What is the variation? And indeed, that is the line of trust. So if I now connect all these, this is the line of trust, right? This is how the slices or wedges interact. This is where the forces are applied one wedge to another, or one slice to another. So in GLE, Morgenstern price assumption is giving you a function that could be any shape. So going back to this guy here in the lower right corner, Jambu's method, it wants you to give an assumption. So by looking at the figure, you're looking at the slope, you already know, you should be expert enough to already know how that slope will behave, so you can assume some kind of a function, and that's why I was asking this little exercise here earlier, that you draw a shape. So if I have a slope, something that's making it a little bit more complicated, something like this. Failure surface is something like that. Then, while I'm drawing it, try to think about what kind of a line of trust or what kind of a line would you imagine working for this slope. Anybody? No, not those figures. Now you have to give your own function.
To the baseline, like those two.
Pretty much something like something that goes like this. We have to sort of somehow follow that its speed there kind of flattens out, it goes up, and maybe it goes down a little bit, and it goes up. You have this reverse curvature, this kind of hump in there. So, it sort of follows the shape of what's going on. Let me ask you another one. How would this one look like?
On this line.
Well, it kind of comes down and then maybe it goes out like that. So use your imagination. That's related to this.
We have to define the function.
Yep. Jambu's method only works if you define the function beforehand, before you start the analysis. Of course, if you assume something ridiculous, then don't expect to good results. So that's why these methods are getting a little bit more and more involved, because they require much more sort of background and expertise to use them. And this method claims overall moment and force equilibrium. It says nothing so far about per slice equilibrium. Right? So the setup is fairly similar to what we've seen before. We have a slice or a wedge, certain width, certain weight. We have the length along the failure surface. We have the interslice So the normal and shear forces, they are applied now at a certain location, and this HT is coming from these distances. So if I pick this one, these are these distances. And they, of course, they vary. So you have a full liberty of specifying them at these distances, whatever they are. And as you see, sort of this line of thrust is going through all the slices, and even though it shows it that it kind of touches the failure surface for the last slice, it doesn't really matter where it's exiting because there's nothing next to it, right? So it doesn't really matter where this kind of comes up like I drew it or it touches the failure surface. It doesn't matter because it's the last slice. General setup, we have the inclination angle. And it's, at this point, I can sort of ask you if you want to do it on your own, but maybe not. That the steps are the same. You have the weight, you derive what the strength is along the failure plane. Exactly the same steps. If I flip to the next slide, this is exactly the same what we had before. What is the shear strength, Mohr Coulomb equation? We divide it by the factor of safety to get the mobilized shear strength. We set up the two forces, normal to and perpendicular or tangential or shear. On the base at the failure plane, we divide T, we plug in this, divide that by the factor of safety. So this first step is identical for all methods. Next step, we start working on what we have as far as Jumbo makes an assumption when it comes to the problem. And in this case, resolved vertically. So if we look at it, sum of Fy is equal to 0. The equation, right? And this is per slice. So we have the normal component, tangential component is equal to the weight minus the balance of the interslice shear forces. So if we go back, we have the weight acting down. We have component of a P being positive. So with respect to W, it's negative. Component of T is again acting upwards, so it's the same direction as component of P. And we subtract, we don't know what the sign is, but we subtract the difference of the two interslice shear forces of XL and XR, whatever they might be, and then we basically set up the equation. And now we can expand it by simply, just like before, for T, we plug in the equation that's there, rearrange it a little bit, and we get a form that's very, very, very similar to previous methods. So the CF means compare. So keep this equation in mind, and let's go back to GLE. There, that equation. Almost exactly the same. Because so far the method did not include anything with respect to the interslice shear forces. It just said that whatever the difference would be. Now, Jumbo's method resolves things parallel to the base of a slice. So it's neither vertical, not horizontal. This is parallel to the base of the slice. So this is new. No other method did anything like this. So along the base, we have T, right? It's acting along the base. We have now the difference of the interslice normal forces, its component. And on the other side, we have a portion of the weight and a portion of the difference of the interslice shear forces. And if we work with it, we can isolate the difference of the interslice normal forces as a function of everything else. For T, we substitute the equation. We have the sort of the mobilized shear strength expressed as a force. And then Jumbo takes a moment about the center of the slice. So again, a new statement particular to his method. If we take moments about the center of the slice, you end up with this equation. If you isolate xr as a function of pretty much everything else, now take a moment about the center of the slice. That would be somewhere you would have to find it, right? So it is some distance, something there. So one of them would cancel out, say if the center of the slice is taken there. So in that case, the moment arm for ER, I believe, just see. So for EL rather is 0, therefore it cancels from the equation. So if we take moment about this line, he says this is the center of the slice. So if we take moment about that point, this one here, then the moment arm for EL is 0, right? It goes through the line of action of EL goes through it. We have ER, whatever the distance is, and so forth, and we end up with that equation that we can solve for XR. Now, Jumbo also claims, remember in the first slide, it says overall moment and force equilibrium. So that equation can be put together, overall force equilibrium, if there is no surface loading. Right? We talked about this last time. If there is no surface loading, if you put all the slices together, what happens? What is the sort of the physical interpretation of this line? If I put all the slices together, what do I have, if anything?
You have the whole slope.
Do I have anything left? And if I put all the slices, put it back together, are there any other forces that are on it? No. That's the idea, right? So it's an equilibrium. So if I put all the slices back together, there are no other forces. That's why it says in absence of surface loading. If I have surface loading, then that equation doesn't hold. It's not 0 anymore, but it has to be equal to, if it's a vertical one, it has to be equal to the whatever this guy here, or if there's a horizontal, it has to be equal to that one. So, I might ask you to modify this method if there is a point load somewhere sitting on a slope. So then you come and you make that one of them the appropriate one non-zero, and then you carry that one further. So if I have now this condition, it means it's being in equilibrium. So I can say that whatever there is internally, I can have the rest of it, and it still has to be 0, right? And if you have surface loading, then this would not be 0 at the end. So this equation, or equality sign, ensures equilibrium, and it's an equilibrium with, in absence of surface loading, with 0. So from this one, this long equation, a lot of things cancel. You would be able to retrieve the factor of safety for force equilibrium. It's this. Any thoughts? Any questions? Yes.
And why would be designed like any slope with the absence of surface loading?
A natural slope that's sitting there.
Like, is it 100% safe to design it with that absence of any unexpected surface loading somehow?
It's somewhere out in a backcountry in a reservoir of hydro dam, and you want to know what this factor of safety for that natural slope is. You don't expect any other loading to be on it, that kind of stuff. Okay. But generally, what kind of a surface loadings do we expect?
On the natural slopes?
Like any kind, it doesn't have to be natural. Like in absence of surface loading, so what would be a surface loading? Like a building, yes. Roadway. Anything. Okay, so this would be the equation for the factor of safety for surface loading, or without surface loading, for forces. Now, how do we solve it? Because of all these assumptions, The solution process is not that simple. It is an iterative solution. So it is first assumed that there is no net. For one slice, there is no net unbalanced shear force at the boundaries. Then you can calculate a new iteration, which is not going to be zero anymore. And then you put it back and you calculate and you calculate and you calculate till the two factors of safety are equal. So what I'm saying is that basically, let's go back here. There. So you go with this condition, you plug it in, you calculate one iteration. Of course, it's not going to be balanced because you don't know a quantity, so you assume it to be zero, and you get some numbers for it. So you just go back to here. You get a quantity, then you feed that back into the equation, you go through the steps, you get it again. So this is similar to the method that we had for Bishop's method, where the factor of safety was on both sides. Everybody confused enough? Good. So, let's look at the equations themselves right away. So, one key equation is this one. Look at it as one quantity. This is the net interslice force. So, go back here. So, this is EL minus ER or whatever. That's the net interslice normal force or the force in a horizontal direction. XL minus XR would be the net interslice shear or vertical force. I don't know what they are, right? I don't know what they are. So I'm assuming that the difference is zero. So if I put that zero, I know everything else in iteration, calculate it, I calculate some value. Then I can put that in another iteration and calculate it again, and again, and again. Till from one step to another step, there is no change anymore. This is simply because I know that if there is no surface loading, the sum of their differences has to be zero. But it doesn't mean that there are zero per slice. So I'm starting with an assumed value of zero, right? And then compute EX, E and X, and then plug it into the equation till I'm sort of rolling over it over and over, and it satisfies the equilibrium. And again, do not fear, you don't need to calculate anything in this course. Okay? And why you don't need to calculate it? We went through this exercise a couple of times throughout the course. So why not? Yeah.
To finish this, you need the whole lifetime.
Yes. As long as you see how it's put together, because now what we're going to start talking about is the actual accuracy of these methods. Okay? So from the theory, and these things we sort of take it for given, right? So let's just review them. Each point within the soil mass must be in equilibrium. Right? There are no soil particles flying out on their own and that kind of stuff, so everything is in equilibrium. That's sort of given. Stresses within the soil mass must be equal to stresses applied to the soil. So the first one is sort of like internal equilibrium. The second one is equilibrium between internal and external. Right? Make sense? Yes, no, maybe. I don't see many nodding. I mean, these are basic assumptions of statics and mechanics of materials. Number 3, strains occurring at a point must be compatible with strains at all surrounding points. It's like a continuity of strain. right? There are no basically ruptures within a material or anything like that. The strain changes sort of in a fashion that the material doesn't tear apart or no sort of material disappearing inside it or anything like that. Strain gradually changes from one point to another point. Strains at every point must be related to stresses by an appropriate stress strain or constitutive relationship. So what does that mean? So think about it. What does that mean?
The N is constant for each section, for each.
It doesn't have to be constant, but there is a relationship between stresses and strains. I know what the relationship. One of them would be E, right? Young's modulus, but it could be some other relationship. So those of you taking soil behavior, enlighten me. What would be other relationships?
I mean, effective stress and deviator stress.
Relationship between stress and strain. Okay, that's E. Are there any other ones you guys learned about between stress and strain?
Well, there's the chemistry model that we use, but that's not exactly.
Like hyperelastic, hypoelastic, stuff like that, no? Okay, so let's stick with there is a relationship between stress and strain, whatever it is. For the simplest one, it could be anything in life. Slope, whatever, Young's modulus. So that's what that statement says. Failure criterion for the soil mass should not be violated at any point. So let me ask again, soil behavior class, what is a failure criterion? I know that we have a midterm tomorrow, so it's a good thing. What is, name a couple of failure criterions for soil.
What do you mean by failure criteria?
Failure criteria.
Of the soil failure?
Yield,
Yes.
whatever, yield function.
Also, you have your failure surface, and if you go beyond it, then your deformation will lie in the elastic region more. So you'll have like plastic strains.
So, now some names for yield surfaces. Yield functions, failure criteria. More Coulomb, Chem clay,
Modified.
modified fine clay, Drucker Fragger. Yeah. Then we have strain hardening, strain softening, past the yield point and everything. So, again, I've heard some interesting things. So let me just draw more Coulomb. The usual sort of formulation of this would be normal. This would be shear. So draw something like this. I'm going to draw 3 points. Call this A, call it B, call it C. Which one of those points is not possible ever to achieve? A, right? That's beyond the failure surface. So I can have C is in the elastic range, right? So if I get a combination of stresses that goes up to the yield surface, what can it do? You say I'm increasing the normal stress. Fail, okay. And which way it can go? I keep increasing the normal and shear stress. It fails, it yields, and it basically starts moving along the surface. It never goes above it. And if I take off say the shear stress, then it can go below. If I load it up again, it can move along. Good enough review for tomorrow? For the rest of you, it's kind of general review of what I meant by yield criteria can never be violated. Good? Now, the limit equilibrium, it was the first method that established that there's a collapse mechanism. What do I mean by collapse mechanism?
The failure happens.
Exactly. That's how the slope collapses. In its crudest form, as it is limit equilibrium, you have a bunch of blocks or these slices, and there's a mechanism of movement of these blocks and slices that is actually what I call the failure of the slope. And if I had the simplest one possible, I would draw something like this. So there's a triangular block of soil that basically slides down. Right? That would be the collapse mechanism for that. Right? And of course, you can now think of it that each one of these would be a block. The way we treated them, if the weight of this and everything comes down, it pushes the next one, and that's what we say as failure of the slope. Yet it's still, it is just, and even for the fanciest methods of GLE, for example, it is still considered the slope nothing but an assemblage of blocks. It gives no information what's going on inside the block. It gives information what's happening at the base and at the boundaries next to the other blocks. Now, of course, you can take this to the extremes and have a lot of these slices, really skinny ones. You know, more slices you have, perhaps more accurate it will be. But it gives no idea what's going on inside. And this last statement, I'm not sure if everybody can appreciate it, that it's neither an upper bound nor a lower bound. This comes from plasticity and all that, so I'm not even sure if that kind of stuff is covered in soil beginning here. No way. So this statement, it says that the limit equilibrium method, it violates a bunch of assumptions of a behavior of a continuous material, as soils are, right? It's not a set of discrete blocks, as for example a rock slope is. So limit equilibrium, it's relatively simple, and you may beg to differ between 2 weeks, but limit equilibrium is a pretty simple method. It doesn't need anything beyond basic statics, mechanics of material, and a little bit of soil mechanics. Even the most complicated is some of forces and moments and shear strength and that kind of stuff. But if you compare it to a real slope made out of a real sort of continuous soil material, it does not behave as a bunch of blocks. Even not 10, but maybe 1,000 blocks put together, it's still not a continuum material. So limit equilibrium is it's somewhere in between. How far it's off from something that's being an upper bound or lower bound solution, you don't know. It's somewhere in there. It's not outrageous, but it's not physically accurate. That's what the statement is. So let's consider now a somewhat more complicated problem of a fairly simple slope, but we have now a weak seam at the base. Right? We have a weak material. It says C equals 0, phi equals 10, whereas the slope itself is made out of a C is whatever, almost 30 kilopascals, and phi equals 20. Unit weight is the same. We had a piezometric line or a phreatic surface that kind of comes down and daylights at the toe of the slope. And it's a 2-to-1 slope. So you see right away that consider two cases. A circular failure surface, that's case 1, and case 2, a non-circular failure surface. Okay?
In the first case, we don't have the weak layer.
Well, whether we have it or not, it's irrelevant. We have to use a circular failure surface. Right? So, what's the implication of having a weak material and using a circular failure surface? We talked about it earlier. Will the circular failure surface method find it and take it into consideration to be horizontal seam or not? Yes, no? While you're shaking your head, so you're right, meaning no, it won't. So it's the same problem, but if we have a tool that only does a circular failure surface, we'll see how well it works. And then we're going to have a tool that can do a non-circular failure surface, so part of a circle, horizontal, and a low part. Right? So we'll see how they perform. So that's a sort of a real case. And what we have here is the various sort of combinations of cases. So what is shown, and let's go it one by one. These are two programs at the time, and when was this? 77, a long time ago. Two software programs that started to implement these functions for the Morgenstern price. So what f is and what lambda is, right? Let me just flip back a few. So those programs has the various options for these. What is the actual value of the function and what lambda is. So if we're looking at it of what works and what doesn't. So two programs, a constant value, so these are a horizontal line for the f, or the half sine, right? Curve, constant, half sine, and a clipped sine is basically it goes up horizontal and comes down, which is, just go back to show this one. So if I would clip the top and make the top horizontal, that would be a clipped sine. So it's something like this, but the sides are curved. The top is flat. Okay, so they use those two for the slope, and let's look at the cases. So case number 1, 2-to-1 slope, 12 meter high, friction angle, cohesion. So this is the case that has no weak seam considered, whether it's there or not, it's a circular. So factor of safety was, let's glue all the methods. 2.08, 2.08, 2.07, 2.07, 2.08. So what can we say? Is the actual shape of this function relevant? Not much, right? Whether it's a constant or a half sine or a clipped sine or anything like that, the factor of safety is about 2.08, 2.809. So it's not that relevant. Now, let me ask you the question. Is it a, you have to look at two things. And I heard, well, I'm sure that you heard too, and I heard that you heard this in concept of accuracy and precision, right? What is accurate and what is precise? Yeah, I know, he remembers it. And shaking his head.
I don't remember that.
You know, I'll draw it. I mean, everybody draws this for some reason, so I suppose. Bullseye kind of stuff. Something like this. So this is the value what it should be. And I get values here that I'm calculating. Let's set number A, and let's get set number B, and let's get set number C just for fun. Let's see. So, set number A, is it accurate? Is it precise? Okay, so it is precise, right? The values do not differ from one another. Is it accurate? No, it's very far from the center. Let's look at B. It's neither, right? It's spread out all over. It's not really precise, and its average is very far from the center. So it's not that accurate either. And then C is, it's clustered around the volume that it should be on. So in the context of this, what do you think? A circular method using it, is it accurate, precise, both, neither? Is it precise? Look at the volumes that we got.
Yes.
Yeah, it's fairly precise. It's 0.08 or something like this. Now, if the weak seam is there and we use the circular failure surface method, we may or may not be accurate. We can only say that if we do another analysis, case number 2, with actually considering a weak seam with a non-circular failure method. And now let's look at the numbers we get. 1.39, 1.38, 1.37, 1.37, 1.36. Is it precise across the volumes? Yeah, it's fairly precise. It's around 1.38, whatever. 1.37. Now, let's compare the two volumes. Different assumptions, circular, non-circular. Which one do you trust more when you look at the actual slope and having taken about 80% so far of this course?
Second one.
Yeah, we say that the presence of the weak seam greatly influences. So if we adopt now the second one to be a precise and accurate answer, then we can say that the first one with the circular failure surface assumption is not that accurate, right? It was precise, but it was precisely wrong. So different assumptions, different mechanism of failure lead to a different factor of safety. So, if you're not aware of this and you're assuming that, I'm just going to use circular failure surface, you run the program, you get 2.08, you tried a bunch of different methods, it's 2.08 because all the methods say it's 2.08, so it's precise. I'm good. Whereas it's precisely not accurate because involving much more of the actual failure mechanism by considering the weak seam, the factor of safety is, considerably lower. Is everybody okay with this little mental exercise? And now there are other cases. I never talked about this RU. This is sort of an old-fashioned way of incorporating water pressure. So let's not look at 3 and 4, but let's look at 5. So it's same as case 1, but now I'm incorporating the piezometric line, and what this one implies is that at the base of any slice, if I have a slice running down here, at the base of any slice, I always know what is the height of the pore water pressure, which is the distance between the base, center of the base, and the piezometric line. So I can now add the effect of water pressure, or U, which I basically subtract, and let's just go back for review. If I have the pore water pressure values, then I can always put them in here, right? I'm reducing the shear strength. So now let's look at the inclusion of the water pressure. What difference does it make? So I'm comparing 5 to 1. So 1.83, 1.83, 1.83. Again, they are precise. They're lower than that one, which is expected, right? I'm reducing the water, or reducing the shear strength by the inclusion of water. So these are the little checks that you look at it, but on the other hand, they are, still they're precise, but not that accurate. And if now compare 6 to 1, 1.26, non-converging will basically is that the method cannot find a solution. Talk about it in a moment. 1.25, 124.5, 124 something. So it's about 1.25, right? So compare it to 1.38. Again, the effect of the water pressure is represented by lowering the factor of safety. Now, this non-converging, if you have these two programs and if one of them just not giving you a solution, what do you say?
Use another for another shape.
Yeah, you know that the method works, so if it's non-converging, I would suspect that there might be a bug in there or some kind of an implementation feature that's not really trying to solve my problem. So, if I look at the half sign and I have another program, just like he says, this implementation, it worked just fine, and it gave about 1.45 or whatever. Anything anomaly like that, you have to investigate why it's happening. Either you goofed something up, or the program is, not working. So if you have another program and you do exactly the same and you get an answer, then there is your question.
So what we have to take from this table is that it doesn't actually matter the shape you use.
As you see, it doesn't really matter for this problem. Now, my next question would have been, and he asked, why doesn't matter? Look at the choice of the shape functions. If you could pick only one shape function, which one would you pick without knowing whether they work or not? A constant, a half sign, or a clipped half sign? Leaving you the little figure here. So we have one vote for a half sign. Okay, we have one vote for the clipped sign. Any votes for the constant?
Yes.
You have
It's
to.
this one, yeah.
Well, look at the shape, and can you imagine these interslice forces, right? They go along a curve, so it's not really a constant, right? It's not really a flat. So half sign, I don't know about clipped, but there might be a horizontal component a little bit here. But this is what the intuition will give you. You follow the failure surface if you know where it is. But as it turns out that the difference between the constant and a half sign is basically not too much.
If the periodic line was lower, it's going to be the constant, right? Below the.
I don't know. I don't know. I mean, the phreatic line basically reduces the factor of safety, but it is the shape of the failure surface that gives a good indication of what's the shape of the function approximating how the forces between the slices are inclined. Okay?
How would you draw the constant?
You could have let me draw a constant.
Maybe for this.
Well, I'll draw it. In the constant would be like here. Horizontal. Right? It's not inclined.
I'm just supposed to be connected.
Well, you can connect them somehow, but it sort of doesn't make sense. Because these are just like meter slices. So the constant for anything like this doesn't make much sense. For this one, I could say it's constant, with the exception of the one in the bottom. That would be on the same line, constant value, right? But it turns out that in these calculations, in this study, it didn't really matter that much. But in some cases, it definitely matters. Any questions about this little mental exercise and what the values mean? As far as precise, accurate, and knowing what the physics would be. Questions? Now, I mentioned it earlier in the course when we talked. Your question? Yes. Like a half sign is, let's just go back here. So this is basically the sign, the half of a sign, right? The other half of a sign is down here. So this is the half sign. So if you look at it, that it starts off inclined, that kind of tapers off, becomes horizontal, and then goes the other direction, which is kind of following the shape of like something like this. This way, that way, horizontal. Okay? So I mentioned this back when we talked about Bishop's method and the complications, that how do you deal with heterogeneous materials? So what are heterogeneous materials? Yeah, they're non-homogeneous. Excellent. What are non-homogeneous materials?
They have different behavior in each direction.
You didn't say anisotropic.
They are made up of different constituents.
They have different properties at different points. If I would have said anisotropic, then it would have been directions, right? Or so what is isotropic?
Same in all directions.
Yeah. Students often confuse direction and position. So, heterogeneous materials, and if you think of it that way, most of the time what I'll be drawing here is one single material comprising the slope, right? It's one homogeneous slope. Now, in reality, unless in most cases you're dealing with a constructed slope that is built out of the same material, right? It's a homogeneous slope, right? And which is okay for constructed ones. But oftentimes natural slopes and even constructed slopes are engineered that different materials are at different levels for whatever reason. So based on this course, give me an example of a structure that's heterogeneous slope. It has heterogeneous slopes. 2 words. Exactly. Embankment, dam. Why is it heterogeneous? Don't tell me because it's not homogeneous. Good.
The foundation is on rock.
No, just the structure itself.
With different layers of material.
Yeah, we have a rock shell, we have filters, different material, different properties. We have the core, very different material. So that would be a, if I just draw it for the fun's sake. if I have a slope stability issue or something like this, that's the failure surface. Then it goes through, maybe it's frost cap, whatever. So you have like 1, 2, 3, maybe 4 different materials, right? So if it's a constructed slope, if it's a natural slope, then definitely its geology is dictating what are the various layers in it, different kinds of soils or even rock, and so forth, giving rise to heterogeneity. So now, these soils, if they're soils, well, even if it's the same material, its certain properties can be non-homogeneous or heterogeneous. Why? I'm kind of hovering the cursor here. The same material, but it has different properties because, water content, how saturated it is or what is the moisture content. It's the same sand, it's saturated or not saturated, it has different unit weights, for example. It may have different shear, whatever, friction, anything. Okay, so it's the same material. And of course, if they're completely dissimilar materials, different cohesion, friction, unit weight, whatever. And as you saw in the derivation of all of the equations, different material properties definitely affect the weight. So if I have one slice here, and I'm going to draw a different color chalk, I'm just going to draw one slice. So if this one slice is made up of a block of this material, a block of that material, a kind of curved bottom, explain, derive, add to some of the method, that kind of stuff. Compare two methods, give me a situation where it will fail, or I give you a situation and tell me what would be the appropriate method to use, or could you use or could not use something, and so forth. Okay, so it's just like first midterm, writing. And some students every year come away from this course slightly disappointed, but we haven't, like you guys, haven't used software. You have to keep in mind that these graduate courses are not about using software. They're about teaching you what the software does. So when you use the software, if you use the software, you know what it does. And so we will see today that you have all sorts of options. It's simple to click the little buttons and get results. Sometimes the results are completely useless. You're the engineer. If you goof something up, it's not the software developer to blame or the company. By using the software, it's your understanding that you take responsibility of what you do with it. Okay? So we'll click some buttons after that. But going back to finite element methods of analysis. So what we talked about so far in the course, as far as slope stability is concerned, it only dealt with something very fundamental and simple. First year undergraduate statics, sum of forces, sum of moments, and basic soil mechanics of failure surface, shear strength, and so forth. That was pretty much it. If you understood those, hence I had the quiz, then hopefully by now everybody appreciates why I had the quiz. Because we needed the material. So whatever we did so far, slope stability analysis, was all based on the same thing. You're summing forces, you're taking moments, you set up equations, it's the same procedure. You have a slice, you look at its base, you find shear and normal forces, you satisfy whatever the particular method says about equilibrium conditions. You have factor of safety, which comes in as the mobilized shear strength. You solve for the factor of safety, and there you have it. That's it. Now, finite element is, and again, I do appreciate that most of you know little about finite elements. Those of you who know some, you wish you hadn't, right? How many of you know something about finite elements? I mean, I asked a couple of weeks ago, some, it's not as simple, put it that way, as driving equations and all that. It involves a lot of math, and the solution procedure itself is much more complicated. But it is a very useful method. Now, in order to use it for slope stability analysis, we have to define a couple of things. I mean, it all goes back to the finite element method of what it does. Most of the formulations of finite element method used in at least this part of engineering calculates deformations, calculates displacements, right? That's the fundamental quantity it's calculating. So if I calculate in a slope that I set up as a slope geometry, I calculate deformations. That doesn't tell me too much about factor of safety, right? It deforms so much, and that's about it. Now, I have the possibility from deformations to calculate strains, and with the constitutive model, calculate stresses. And still, nowhere in there is any mention of how do I get factor of safety out of it. Okay, so you have to keep that in mind that finite elements don't give you the factor of safety right away. As in, say, limit equilibrium method, you solve for factor of safety and you get it. Now, the fun thing with finite elements is that I can have pretty much any kind of a stress-strain relationship. Non-linear, linear, whatever. So the step between strains and stresses, I can use whatever other methods there are. That's a fundamental difference. For most, and I'd say 99.9% of limit equilibrium-based slope stability is based on more Coulomb failure criteria, and that's it. As you saw throughout the derivations, in one of the first steps, and I just go back wherever this me spinning the little wheel on the mouse stops, like at here, Jambus, fundamental is the more Coulomb. Now, everybody appreciates that there are many other methods for failure criteria for soils than more Coulomb. So what about those? Well, limit equilibrium, unless you derive it, if it's possible to derive it using any of those other ones, it doesn't exist. Now, the fun thing about finite elements that it is basically built in. I can have, by definition, any kind of a stress-strain relationship or a failure criteria put in. Yet still, no mention of factor of safety. Okay, so still keep that in mind. I can model certain funny things I couldn't even dream of doing in limit equilibrium. I can model progressive staged construction of embankments or excavation of slopes or anything like that. I can subdivide, and if you think of it that way, those of you taking construction engineering, how deep can I excavate with these land or earth moving equipments in one shot? Anybody? I have these bulldozers, I have these earth moving equipment. How much of material can I excavate? One layer. Or like depth-wise. Yeah, so I'm fairly limited. So if I'm excavating out a slope that's 20 meters deep, right, I cannot do it in one shot, right? I'm, let's say, 2 meters or a meter, let's say 2 meters, a 20-meter slope will require me to take the material away in 10 different layers. Agree? All of the slopes we looked at so far, I said, okay, well, there is a 20-meter slope. What is its stability? Well, slopes are not just created like that. They're excavated, they're the same idea if I have earth-moving equipment. They're constructed, they're embanked. And let's say I can embank material, raise material in 2-meter heights, but generally much less. But anyway, let's say 2-meter heights. So a 20-meter embankment built has to be done in 10 lifts or 10 stages or 10 layers. Now, The question is that if I can calculate what is the stability of a 20-meter slope, given whatever conditions, by the time I get there, either via excavation or embanking, are there any slope stability issues while I'm constructing it? There might be, right? So let's say that the situation where the water table is at ground level and I'm excavating downwards. I'm creating a slope that is, you have a perched kind of water table that's draining out. It changes the slope material to be an undrained condition. And it might fail at 3 meters. You never get to the 20-meter depth. Now, limit equilibrium, you would need to model each and every those steps separately and see what's going on. But the other thing we do have to appreciate is that the stresses do redistribute rather with excavation or embankment because I'm piling up material or removing material. And so does the groundwater table changes. Now, with finite elements, I have the liberty of basically simulating all that process in stages. 2 meters, I make 10, like within one model, 10 stages where material is being embanked or material is being excavated. And I can each step, depending on the previous steps, I can have stress redistribution, I can have redistribution of the groundwater table, pore water pressure, everything. That's part of the finite element method. Like I said, I can't even dream of anything like that using limit equilibrium methods. Now, in addition to that, I can have material that's cracking, tension cracks, disintegrating basically as excavation is going on. I can simulate hydraulic fracturing, hydrofracturing. I can have local failure along part of the failure surface, not necessarily the whole failure surface. I can have multiple zones of failure that will eventually combine to form the failure surface that's, nothing circular or anything like that. Finite element can do that. Limit equilibriums cannot. Now, of course, like anything else, it doesn't come free. I put one aspect of it, the high cost as far as time is concerned, and I don't only mean like the analysis that it takes much longer to compute, but it takes much longer to actually create the model. And what I mean by that, it takes much more expertise to create the model. As we will see, there are much more steps. Yet still, now there are 5 points here with all the wonderful things and everything, yet there's still no mention of, okay, I run one of these analyses. How do I get the factor of safety? That's the big question. So, before we even define it, which is inherently attached to it, I have to sort of reformulate, reinterpret using finite elements what it means that the slope or the material fails. Okay, so for limit equilibrium, we went through this in rather detailed steps of what is failure. So anybody can summarize it of what do I mean using limit equilibrium, factor of safety, what do I mean of failure of a slope? Yes, the factor of safety is 0 or just below 0 by, a thickness of a hair, like 0.99999, whatever. Anything less than that, it should not exist because it failed, right? The forces acting on it are much greater than what the forces are there to hold it together, the shear strength. Now, in finite elements, it's much more complicated of what is failure. So I list a couple of ideas that what do I, and this is really going back to the idea of an much higher required expertise of interpreting the results. What is failure? Is it some magic amount of deformation? Remember, finite elements calculate deformations, displacements. Is it at some amount of deformation that I say the material failed? How much? Is it, a fixed value? No. Also, if I say it is some amount of deformation, where, in what region of the model? It should be everywhere, partially. It's not defined. Finite element solution doesn't give you a result when it comes to that. And is it that the slope fails is when the solution itself is non-convergent? Now, what I mean by non-convergent, the finite element analysis, it basically involves a solution of a large simultaneous set of equations, right? A huge inversion of a huge matrix, and that gets multiplied by the forces that are on the right side. And so the matrix, the stiffness matrix times the displacements equals to forces. So you have to invert that matrix or solve this huge linear system of equations. Now, if the forces are so great that simply the solution is not possible to solve because the stiffness matrix has singularities, it has negative values for the coefficients, or the diagonal has some issues. There are many problems stem from the solution process, the mathematics of solving it. One of them is that the results cannot converge. Okay, so the problem is that it's not solvable, generally due to huge amount of displacements in parts of the model. It doesn't have to be everywhere. So could that be what is meant by failure? It's still not clear up till now. So these would be the issues. So one way to deal with it is something called the shear strength reduction, the SSR method. And it's pretty simple, think of it that way. We've seen this equation in the past. Mohr Coulomb's failure criteria written as the mobilized shear strength, which is the shear strength divided by the factor of safety is equal to the cohesion divided by the factor of safety plus normal stress tan phi divided by the factor of safety. Okay? So if I have a slope, and let's draw a slope, it's always helpful. So if I have a slope, and I'm just going to use C and phi, and gamma, but it doesn't matter. So I can calculate, and let's say for the time being, I define the failure. Let's say it's the maximum shear strain. That's one of the criteria for defining failure. Let's say maximum shear strain . So whatever you calculate in a model, if your calculated value, let's call it A, for the shear strain in a model, as soon as A is greater than what the maximum limit is, and again, nobody says what the limit is, it's really up to the analyst to define what the limit is. As soon as the shear strain in your model is greater than the maximum, you say that, well, that material has failed. So that's my failure condition. So what I can do with the SSR method is, these are the quantities that you assume that the material has, C and phi. You analyze the model, and you assume that the factor of safety is equal to 1. You analyze the model. If the condition is such that A is actually less, not greater, but less than the maximum shear strain, that means that your slope is with the given C and phi is fine. Then let's say you're going to go 1.5. So you divide these by the factor of safety. In essence, you're reducing them. You redo the analysis and you check for this condition. If A is not greater but less than this, then the slope is okay with a factor of safety of 1.5. Then you do this maybe for 1.6. So you divide C and phi by 1.6 according to the equation up there. And in that case, the resulting maximum or resulting shear strain is greater than the maximum that you allow. So in that case, it doesn't work. It failed. Then you go back, maybe you try 1.5, say 1.55. You do the procedure, A is greater than the maximum allowable, not good. Then maybe you try 1.525, whatever, and then so forth until how many decimal digits you want. And then you say that my slope's factor of safety is the number that actually is right next to exceeding the condition of maximum shear strain. So this is how you define, how you find factor of safety. Now the fun thing is that software does this kind of stepping through the numbers automatically. You give C and phi, you press a button, you wait a little bit, and at the end it will give you various phases of the analysis leading to where the factor of safety is found, i.e. giving you the maximum condition in which the shear strain is not violated. Okay? So we'll look at it, once we get to that in a computer. So just to recap, so you have a starting cohesion and friction, you analyze the slope, and you find whatever the maximum total displacement is. We know how to relate deformations or displacements to strains. That's a relatively simple equation. Like, what is strain? Let's say, let me just draw a very simple situation of a one-dimensional case. I have 2 points. I know distance is L. I do the analysis, and let's say both points can move. And now this distance is L1. What is strain?
It's the change in length over the original length.
Yeah, so it would be L1 minus L over L, right? So this is not shear strain. It doesn't really matter for this course. This is just strain along this one direction. Okay, so this is strain. For shear strain too, the equation is pretty simple. So if I find the displacements from the finite element analysis of where these 2 points move, I can easily find strain. So the SSR works that I find the maximum total displacement. Total is basically the magnitude. We have 2 dimensions, so it's the square root of x squared plus y squared, right? The length of something. Now, I reduce by the next factor of safety until I cannot find the solution, meaning that there is just so much displacement that your finite element procedure falls apart. So if I were to put this in a little figure, it would be the horizontal axis would be the maximum total displacement, and the factor of safety that I'm using in the equation would be on the vertical axis. So for every step of the model, by reducing the factor of safety, there would be a maximum total displacement and a calculated or given factor of safety. And I will end up with a curve that sort of, at some point, it just kind of flies off. There's a huge change in displacement, and I cannot find the solution. So that is taken as the factor of safety for that particular slope.
It's not until it reaches A.
Well, A is when this condition of non-convergence occurs. Like you can't find the solution. Okay?
So that's when you know A. You don't say equal. It's just once you can't find the solution.
Well, A is basically calculated from an equation. Like A is the shear strain in your model as a result. When it becomes so great that you can't find the solution anymore, you stop. But this is one interpretation. There are many interpretations of what is failure, when should I stop. This is the SSR is the most prevalent way of looking at it, and it's been proven that the factors of safety and the location of the failure surface obtained via this method closely corresponds to the ones documented as basically failure cases, and also it's very similar to the ones predicted by limit equilibrium, where there is a correspondence. But keep in mind that finite elements can do much, much more. Okay, so any questions about the finite element base? What I want you to know is, what are the differences between finite element and limit equilibrium? What is that finite elements can do extra that limit equilibrium cannot even dream of doing? But what are the difficulties, and mainly trying to figure out what is meant by failure? Is it a huge amount of deformation? Is it a deformation that, leading to a certain amount of shear strain, or what it is exactly? That's not that well defined. Because you can have situations, and I don't have any model that I can show you, but one of my students, she's doing slope stability with loads and a slope, and really causing issues. And let me just illustrate in a few words of what the problem is. Now, most of you took an undergraduate foundation class, right? You know what the foundation is, you know how to design it. Basically, it's a localized shear or some kind of a shear failure. So if I put a foundation on the top of a slope, this thing can fail in multiple ways. One of them related to this course would be that there's so much external load that it leads to a slope failure, right? External loads. Makes sense. Now, what would be another way that this foundation can fail?
The foundation itself is right.
Building? Yes, well, there could be some kind of a localized failure, either by forming this sort of shear failure that never gets to the slope, or it could be somebody mentioned like local punching type of a failure. Okay? If you've never taken foundation engineering, believe what we're talking about. If you did, you know much more than what I'm trying to say. So what I'm trying to illustrate is that for a foundation near a slope, the foundation can cause slope failure, or it can fail underneath the foundation by a general shear failure or bearing failure, or a somewhat more localized punching or crushing of the soil underneath and failure. And these type of failures do not affect the slope. The slope will not fail. It's just the soil under the footing fails. So what's the interesting thing is that she's doing finite element analysis of this and trying to capture varying the distance between the foundation and the crest of the slope and the height of the slope and all that. And some of the results, the software is giving basically, to her at least, crazy results. Right? So you have to keep in mind what the software does. The software stops what is shown on my slide, that this is the displacement maximum, and when it reaches the displacement is so big that it stops converging, that's when the program says, well, this is my factor of safety. Okay, so this is what we talked about for slope stability. So, What's happening here in this case is that there is so much deformation under the footing that the program thinks that, okay, this is the maximum, it doesn't converge, yet she says, oh, but my slope is stable. So that's when she started to realize that, well, there could be two kinds of failure, slope failure or foundation failure. And what differentiates them? So you have to be really careful of what the software is giving you. She's showing me screen captures of the software that, there's a huge amount of shear strain underneath, and it fools the program, or it doesn't. The program stops, and it has the factor of safety for the slope of maybe 2.5, yet it stops. So that's what exactly the program is right. It stops because it exceeded this maximum displacement, maximum shear strain, but it did not affect the slope, it only failed the soil underneath the footing. So when you're using software and all that, you have to have a really good understanding of what's going on and how to interpret the results, because otherwise it's nothing but pretty pictures, as we will see. Okay, so let this serve as a cautionary example of you have to understand what's going on. Okay, so there's not much really more that I wanted to say, unless you have any questions related to this part of the topic. So I would like to take a break and try to set up my laptop, which may or may not be successful. If it's not, I have to visit the fourth floor, the IT people to hook things up, although it looks promising at the moment. So let's have a break. The usual 10-15 minutes. I hope I'll have everything set up. Let's assume you know absolutely nothing about the software. Okay? It doesn't really matter what company, although this one is called Slide from Rock Science. There are many other ones. They'll all do pretty much the same. But let's assume we know nothing about the software. Okay? It could be anything. What I want to do prior to start using the software is go through this little mental exercise of making a summary of what information we need to carry out slope stability analysis. So it's a good review for next week. Tell me, and I guess to the whole class too, what information we need to have in order to analyze stability of a slope. We have definitely need the slope geometry, right, which is comprised of hold on. Geometry, which is basically what for a slope? It's height, the slope angle, right? If it's a simple slope. So we need its height and we need its slope angle. Or, its height and its depth, and from those we calculate the slope angle, whatever. So that defines its geometry. At least in a simplistic terms. So let's draw this or write it or whatever we can do. So let's define. And while I'm doing this, you're thinking, what are the things we need? So we have, let's say, the slope height, and let's say we have the slope angle. What else we need? Okay. Okay, C, phi, and if there is a water table, how it looks like, whatever. We need that too. What else we need to do slope stability analysis? Okay, let's say we have some kind of a load. Good. I don't know where the failure surface is. Most of the times, it's one of the unknowns. But you're getting close. What is the most fundamental thing is that, most of these things are definition of the problem. There's a fundamental stuff that's missing. Huh? No, something much more fundamental to carry out slope stability analysis.
Foundation
Hmm?
property, the soil, the very
See if I can.
Extended.
Exactly. You have to choose the actual method. And that's one of those fundamental things, is that if you choose the method that's not appropriate, you get results that are not appropriate. So the choice of a method, now the easiest one is, well, we'll see it in a moment. Let's pick all of them. Let the software calculate it and then have fun with it. But choosing the method is important. Now, there are a couple of other things that are important that in order to run the software you have to have, and we'll go through it in detail. So let's just look at this software briefly. It is presenting you basically a CAD interface, some nice white area, and I'm really disappointed in the quality of the projector. If you walk to the back and look at it, it's all blurred out, so I don't think you can read any text or anything like that. Anyways, so you're presented a lot, right? Most of the surface is a white area, that's where you draw. It's basically like a CAD package allowing you to sketch up the geometry. You have a bunch of other options. Up here you have 3 tabs with pointing arrows going from geometry to loading and support to surfaces. So this is kind of indicating, guiding you in how to define a problem. But prior to defining the problem, if we set up the project and look at the various details, I'm not sure how much can you actually read what it says. Can you read anything like that?
Press units.
So I'll just talk about it as opposed to if you can't see it. So one of the fundamental things is programs are dumb. They're excellent calculating whatever you tell them to do. Yeah. Can't magnify the whole screen.
No, just the part that your pointer is.
Okay. Show me how to do it. I'm mainly a Mac person. Okay. Well, this would be more than 100. You make 200. This is going to be fun. So first and foremost, like I said, programs are pretty dumb. So you have to tell it which way the slope is actually failing, right? It can either fail from right to left or left to right. So if I draw, for example, just on a side note, an embankment dam that has these slopes. So you have to indicate what direction the actual failure is anticipated to occur, because otherwise it's ambiguous.
In that case, we should have to do 2 simulations, 1%.
Yes, one for each side. So you define which way so let's say it's going from right to left or left to right, either one of those. Let's leave it. You have to define basically units, what you're going to be measuring things in. Programs are written these days such that they are independent of units. It's up to you to use consistent set of units. So metric system, time is days, permeability, meters per second. Only other options you can have, let's say, groundwater, how you're going to define groundwater. You can define groundwater as coming from a finite element analysis. Or you can define a water table if you want. Water table. Unit weight of water and so forth. Other possibilities, you have seismic forces. Yeah, I haven't really talked about it and so forth. So first and foremost, we're going to specify that we're going to create a slope that fails from right to left. Okay. So now we're going to draw a slope. And I'm just going to draw a simple slope. So it's going to fail from right to left, and this is where it's going to get a little bit scary, because I don't really see what I'm doing. So I just define a boundary. Okay, so I defined a soil mass. Now, what is that we see here that we do not see on a sketch like that, and what is its implication?
Depth below the slope.
Okay, so now I'm defining a certain depth below the bottom of the slope. Now, what's the implication of that?
That curve.
Yes, it has a huge implication. Let me go out to 100% because it's driving me nuts already. A huge implication of this is that, let's say I only made it, I can move vertices in a second. I only made it fairly narrow, or not like shallow. So I made this change. What do you think the implication of this change would be, say, using a circular failure surface method?
Maybe trunk it.
What do you mean by that? You're right, but you have to explain what you mean.
What we see previous classes, that the trunk can have less movement, so it will be less precise for the failure.
Maybe the failure surface exceed the border of the.
Yeah. So by defining something much smaller, you're in essence limiting the area of the or the soil that it's going to look for potential failure surfaces, right? So it will not find a failure surface that's something like this, that goes outside the defined soil region. So it will only, the lowest one maybe will be something like this. So by making this silly choice, you're automatically limiting what the program is going to look for when it finds or looks for failure surfaces. Okay? So it's a huge issue from the analysis that you make this mistake and you're excluding a lot of potential failure surfaces.
What are the boundary conditions? You have to put some boundaries?
Well, you have to, there are no boundary conditions, this is limit equilibrium, right? But you have to define a boundary. How far do you go out? Now, let me do the other extreme of moving vertices. I can go all the way that much down. I can even go further. Okay, so this will now allow something really deep failure surfaces to be formed. And the same goes to the side boundaries. If you make it too narrow, then all the failure surfaces have to be within this, I guess, yellowish soil mass. So it is really your choice how big you make it. There are no guidelines. It has to be big enough. It cannot be too small because you're excluding things. Does it make sense? Yes.
Can you understand what you meant by there's no boundary conditions because
Well, in finite element method, you do have boundary conditions, right? Certain equations that have to be satisfied on a boundary, right? Like Neumann or Dirichlet boundary conditions. In limit equilibrium, it's not an initial volume or boundary volume problem you're solving. What do you mean by boundary conditions? Let me ask you.
Well, fixed point.
Okay, I thought you meant like mathematical equations that have to be satisfied on a boundary. Like this is an unlimited soil mass and this is a slope. There are no defined boundaries. It's just how big of a soil mass you're considering is the question. It's really up to you, but don't make it too small. That's the point I'm trying to illustrate. So we define the geometry. What else we need that we have here?
A water table?
Okay, let's say for the time being it's a dry slope, so we do not have a water table. What else we need?
Assign the soils.
Yeah, soil properties. So let's say I'm going to define materials, and it brings up the little window. And let me zoom it because I see that everybody's kind of screwing over. So I'm defining material properties. I need its unit weight. And I can give it saturated unit weight, right, if it's saturated. I specify what is the strength, what is the failure criterion for the soil. Like I said, we only dealt with more Coulomb. There are other ones, of course, and there's a lot of other ones. Some of them are, say this one, everybody remembers it. Andre, phi equals 0. Infinite strength, something that you do not want to fail for some reason. And also some for rocks, for example, Hooke-Brown or generalized Hooke-Brown would be for rocks. And some, all sorts of other ones that you can define. But, even in this graduate course, we just leave it at 4 Coulomb, which is showing the equation there. For more Coulomb, we need cohesion, and we need friction angle. And if for whatever reason the soil has tensile strength, which is generally the same, doesn't have. So you need these properties. Would you want to? There are programs in conjunction with this one that have basically tabulated properties. This one is called rock data. That's mainly for rocks. Okay. Now we define it whether that material is affected by water. Some materials are not affected or can be made out of. Say it's some kind of a polymeric liner that can break, but it's impermeable. So we believe that. But for generic purposes, we need the unit weight, we need cohesion, and we need friction angle. And then I can assign that material to whatever is slope material. So we have the geometry, we have the material. What else we need? Let's say that we do not have, for the time being, we do not have surface sloping, but we have the possibility of adding loads, piles, anchors, all sorts of stuff we can add. But let's say we do not add it yet. What else we need? Yeah, the method. So let's look at the method. So project settings. So actually, I can get to it from other situation. So in conjunction with, let's not do this. Let's do something else first. Surfaces. You guys scream if you can't see it, because right now this is confusing the heck out of me. This one. Surface there. So, in order to do it, we have to, and I'm going to magnify it now. We're going to have circular or non-circular. Right? What we talked about in a course defines it. How am I going to find the critical failure surface? I talked about this grid search. We'll look at it in a moment, how it looks like. grid search or this auto refine. This is one of those mathematics-based optimization methods that explores an n-dimensional space. So we have to define the grid search. Let's say the grid search, I specify how many increments for the radius at any grid point, and also we'll see it in a moment what we're going to do to define things. So let's accept this, and I'm going to add now the grid. Auto grid, it calculates it based on the slope dimensions. You see this little marker here, and that other little marker there. It knows what the limit of the slope is, so it gives you an idea of what the search area might be and how many points you want within. So I take the default 2020, and it's now generating me this grid. Okay, everybody okay with this so far? We can, let's see what else. Let's not do any of those things. So if you look at the properties, by default, it sets bishop simplified and jumbo simplified. The number of slices is set to 50, right? Everybody understands what that is meant. And anything else, we don't really need anything else for the time. Now let's find the options to add more methods of analysis. Okay, find it. Yes, so just like we said, I can increase the number of slices and I can control the tolerance of, say, bishops, how many iterations it takes to solve for the factor of safety, but generally the method of, say, vertical slices that we talked about in this course, this is what I have. Well, there's more, but I can only show one of them. So bishop simplified, everybody remembers it. The corpus of engineers 1 and 2 is fairly an outdated method. I don't even talk. Another one we like is the GLE Morgenstern price. Let me click on it, and then a new option comes available. What does this option mean? So, yeah, so I have an option of specifying, let's see, constant, right? Everybody remembers that little figure, trapezoidal, half sine, a clipped sine, which has it doesn't go back to 0 on the sides for some reason. And the funniest one, user defined. I can make my own function, just like the one of the entries in the flow table we have. So for the Morgenstern price, let's leave it at half sine. So I have these options now. Which one you pick? Well, you're the one who's doing the analysis. So you have to know. So GLE, jumbo simplifies and corrected. Some other method, we talked about the ordinary method of slices or the Swedish method, or the other name is for Fellenius's method. There's Spencer's method we talked about, and Sarma's method I have not talked about. So let me just go out to, is there a way to set this less than 200? Probably not. So if I hover over each method, it gives me a little bit of summary. So I'm going to read it, because when I zoom in, it doesn't show it. So bishop simplified, force equilibrium in X, disappear, not in Y, moment equilibrium, yes. Let's pick, for example, GLE, force equilibrium, yes, moment equilibrium, yes. Everybody remembers this. Jumbo simplified, force equilibrium, yes, moment equilibrium, no. Jumbo's corrected, force equilibrium, yes, moment equilibrium, no, but there is a correction to it. That's the ordinary method. Force equilibrium, no, moment equilibrium, yes. And finally, Spencer's force equilibrium, yes, moment equilibrium, yes. So everybody remembers what's the difference between Spencer's and GLE, right? So if I ask you the question next week, your answer is going to be Who would enlighten us today?
Well, the difference between the two has to do with the intersize forces, because Spencer says that the ratio of x over e is constant, whereas
Exactly.
Ferguson and Price says that it's a function of x multiplied by lambda.
Yes. Which is basically a half sine, and lambda is a scaling factor. Okay, so you know these, so you understand what it does by clicking the option. So these are the available. Now, if I have non-vertical slices, I can have a bunch of other options. I haven't even talked about these, so let's just not go there. So I define the method. These are the methods I want to consider. I define my slope. I define my search area. I define the material. So we are hopefully ready to do the analysis. And, save it, whatever. I made a folder here. Just, save it. Doesn't matter what it is. Replace it, and comes the analysis. And that was the analysis. It calculated about almost 5,000 different possibilities. And this is, it's a 2-in-1 laptop. I guess 1 or 2 generations ago, processor in it and all that. So, it's basically a tablet PC, and it takes a second or two. Okay, so done the analysis, and where are the results? Now for the results, you have to click another button. So, what's shown here?
That's a probability that the center.
Okay, be careful with the word probability.
I mean, that's where the most centers accumulate.
So this is, remember, this is the contour map of factors of safety obtained by each and every grid point. Let me see if I can turn on the grid point. Probably not. But anyways, at each and every grid point that we have here, right? Each and every grid point, I would have, we said, 10 possible circles. At each and every grid point, it keeps the one with the lowest factor of safety. So if I map those up in a contour map where the factor of safety, the hotter it is, the redder it is, lower the factor of safety, the cooler it is, the higher the factor of safety. So this little map shows me, if I move the cursor, it shows what the factor of safety is, and it so happens that the lowest one is basically a factor of safety of 0.865. That looks something like this. Now, let me show you, if I click on this, this is going to show me all the factors of safety, all the failure surfaces that were the minimum at the grid points. Right? So it considered all these, and they're color coded, so the hotter they are, the lower the factor of safety. But if I now click on this button, this shows me all the surfaces that the program considered. So now comes in the implication of having the bottom boundary, in this case, not deep enough. If it was only this deep, all these surfaces here would have been excluded. So in this case, it's deep enough, right? There are no surfaces touching it. So whenever you run the analysis and you see that there are a bunch of circles against the boundary, that means that you have to enlarge, because it's looking for cases that, that are outside of that particular boundary. So, before looking at various methods, right now it's showing the results for the Swedish method, right? The ordinary method of slices. I have the possibility of turning on all the slices. Remember, we had 50 slices. And if I'm really, 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 really interested, I can pick a slice. Let me zoom in. I can pick a slice, and I can look at the weight of the slice, the normal force, and the shear force. And here, I would be able to look at all the quantities at that particular slice, from the weight of it to the friction at the base, shear strength at the base, shear stress, and so forth. But these are all appropriate to whatever method is being used. Right now, it's the Swedish method is used. Okay, so now let's look at interpret the results that we zoom out. So 0.865 for the Swedish method. Let's see what Bishop Simplify is giving. Bishop Simplify is giving, don't mind this, this is just showing the location of the minimum where the other method was. So Bishop Simplify says it's 0.904. Let me turn off all these other ones. So these are the two failure surfaces. One of them is the black one. This one is for the Swedish one. This one is for Bishop Simplified. So you see that the failure surfaces are not the same, and the factors of safety are not the same either. Now let's look at some other ones. Let's look at Spencer's. Spencer's is 0.898. The failure surface is kind of in that general region. Let's look at, say, GLE. It is basically exactly the same. It's 0.899 and more or less the same area. Yeah.
So you're comparing right now GLE versus the original?
Let me just.
I mean, the original, what model?
The original was at that location, it was ordinary method of slices. Okay? So let me turn off these. So Bishop Simplified, Jumbo Simplified is probably the same. Spencer changes a little bit. You see that the numbers change a little bit. And GLE is 0.899. So we can say with more or less certainty, given these assumptions of a circular analysis, that the factor of safety is about 0.9, give and take. And it is located thereabouts in this region. Okay? Everybody agrees? Good. So let's go back to the model here and let's add some surface loading. Let's add some load normal to the boundary of, say, 100 kilopascals, and let's add it between here to there. Okay? So now I added this, and let's, for the fun's sake, add some groundwater table. Where do I add groundwater table? What's the geometry? Okay, groundwater. So I can add now the groundwater table, something like this. And let's say it breaks out. It doesn't really matter what I'm drawing. Maybe there's ponded water and so forth. So groundwater is affecting all the materials. And let's click OK. So there is some, well, this is not really physical. You see, it allows you to make funny things. Let me move this point. There. So I have some kind of a water surface, maybe there's a wave coming up, and this is the groundwater table. Okay, so I have a load, I have a groundwater table, so I added more complexity to my model, and let's save it. Go up to the zoom, because I can't see what to do. Saving the model, loading it up, calculated it, end of the story. So, comment, let me zoom in. Comment on the factor of safety value. Well, less than without the load and a groundwater table. How about the location of the failure surface? Yeah, you see it's a toe failure. It emanates at the toe and goes up to the crest, including part of the load. Let's see what Bishop says. Bishop says 0.54. It's really at the boundary, so something is maybe not considered all the way. But the location of the minimum failure surface is not what the other one is. So who's right?
You think the worst is
Okay, compared to ordinary method of slices giving me this. Bishop simplified is giving me this. Spencer's is giving me this. And GLE is giving me this. So I can show a bunch of photos like screen captures like this on the midterm next week and ask you what is the factor of safety, which method is right, justify your answer. And this is a practical application of what you learn in a course. You know all the methods, you know their assumptions, you know their deficiencies. So do tell which one do you trust and why. Simple as that. So I'll give you a minute or two to think. Okay. Formulate your answer.
I would choose the first one because I would not risk a differential settlement.
Where do you have differential settlement? There is no settlement calculated here.
Yeah. If the failure is under the load, there you have some.
Limit equilibrium does not calculate settlement. So you're given 5 results of factors of safety and different failure surfaces. My question to you is, which one do you trust?
I read that the ordinary method of safety is not really accurate when you have high water pressure. So, and Bishop and the GL are technically more accurate for effective stress analysis when you have water pressure involved. So, go instead of
Well, think of just the fundamental things that I hovered over these tooltips. We always trust the method that's the most complete and available, right? The Swedish method does not satisfy all of the equilibrium conditions. So it's giving you a number, but that number is based on a set of assumptions. GLE it has all the components. Force and moment equilibrium is satisfied, and in this case, Spencer's and GLE Morgenstern price are pretty much the same. They vary a little bit based on these functions for the interslice forces. But you can't really go with the lowest number. The lowest number might be unjustified. If this is a project that you're bidding for to construct and you over-design it, over-costing and all that, you're going to get into trouble because you're basically wasting money. So you have to know, and like I said, this is what the course is about. Based on what you learn about each method, what's available, you look at the results and then you decide what is the factor of safety that it's giving you. It might not be the lowest, unless you can justify why it's the lowest. So if you look in your notes, and I don't want to hook back the other computer, what does the Swedish method say about equilibrium? What conditions does it satisfy? Exactly. It says nothing about force equilibrium, and I put a big surface load on top. Are the surface loads directly considered in any moment, or sorry, any force equilibrium? No, they're not considered at all. So how could you trust the results? Okay. So, this is the sort of, I'm not saying trick question, but I expected better replies than, taking the minimum or something like that. And even the location of the failure surface. This predicts a toe failure. All the other methods, and we know that by, sophistication-wise, we would do GLE. Now, then the second part of this question is, what's preventing us from using GLE only? I don't even look at the rest of them. I spent 5 minutes saying that, well, GLE is the best. Why I just don't use GLE and forget about that. What's in GLE or Spencer's that you have to do? That you say do not have to do in Bishop's method?
The moment when the force are separate.
Yeah, you have to make an assumption about the shape or orientation of the interslice forces. So you have to make an assumption there that, say, in Bishop simplified, you do not make. It doesn't need. It makes its own assumptions. So it's always, just like I had in one of the slides, you always consider more methods that are all of them are appropriate. And then you look at the results and you see why they're different, what is common between them, and so forth, and then you make a conclusion of what the factor of safety is. So everybody learned the moral of the story? Good. So let's look at a bunch of other examples. I made a selection, but probably you could spend weeks on this. So let's say, just going to go one by one. Oh, sorry, I'm in the wrong program. So this is a typical earthen embankment dam. It has a funny looking core, sloped core. It has a shell and it has a foundation material. So it has a water on one side, but water table is explicitly not defined as it is. So we are concerned now about failure, not only the shells of the embankment or through the core, but actually failure in a foundation also. So let's see what analysis methods were prescribed. So we looked at, again, we're going to look at Bishop simplified, GLE jumbos. I'm going to uncheck these other ones. Spencer's, and so forth. 25 slices, half sine function. Surfaces, this time we're going to use something called well, let me run it and we look at it and I'll explain. Being used by other, okay. It's open in the other. Okay. click twice or something. Okay, so what is it doing? What was it doing? So let's just go back to the problem definition. Like I said, I defined where the water is. I didn't define where the what is. Yeah, I didn't say anything about the phreatic surface. In a model within, I let a finite element seepage analysis to occur, that knowing where the water is, and it will find where the phreatic surface is for you. So let's look at the results of analysis. So now it went through a finite element analysis in which it actually calculated where the phreatic surface is in your dam. So I don't need to know where the phreatic surface is if I know how much water I have in a reservoir and what boundary condition I have. Let's say the water is at the ground surface here. Run a finite element analysis and it will find it for you. So I'm coupling finite element seepage analysis with limit equilibrium slope stability analysis. So once I have the pore water pressure distribution right at the base of every slice, let's just look at it. So pick one slice here. I would be able to now find the water pressure, pore pressure, right? So it calculates now what is the pore pressure at the base of the slice and includes it in the analysis. Or the other one is an option here. So Bishop simplified gave me a factor of safety of 2.2, but is there something missing here? What we had in a previous method. Yeah, there is no grid. So if we do the analysis based on mathematics, what it does is it's searching this. In this case, it's a three-dimensional space, xy location of the circle and a radius. So it's exploring this space and it found centers of circles. Let me find it. Found centers of circles that could cause a failure surface even up here. It's like way outside of any grid that I would think of. But it's a plausible surface. So it's, it's looking for all these various weird spaces, and then it finds the minimum of whatever it was. So I'm just going to zoom back to the area that okay, so the minimum is located somewhere there. So there is no grid. It uses mathematics optimization to find a minima of a function in an n-dimensional, in this case, three-dimensional space. And at each of these centers, these are the possible kind of circles that can be found. And finding the minimum, it's there. Now let's see other methods. Let's say GLE 2.25, that's pretty much at the same location. And let's see, Spencer's 2.235. So there's a little bit of a difference because of the interslice force inclination. And just for fun's sake, let's look at jump is correctly 2.222. So if I go back to Bishop simplified, turn off the slices. So it's 2.19, and this is where it's located. It starts from the crest and goes all the way there. and compare that to say GLE, Morgenstern price, 2.25. So this is a little bit higher, and the failure surface location is almost identical. So in this case, one is 2.19, the other one is 2.25. They're pretty much at the same location. So in this case, I would be okay taking perhaps bishops or GLE. They're close enough. Any comments? So let's look at another one. Like I said, we could probably spend days doing it, but we'll look at another one. So what if we have multiple materials, right? I have three different kind of materials with their properties. If you look at the material properties, soil 1, unit weight, let me zoom in. Unit weight is such, more Coulomb, cohesionless material, friction angle of such. Soil 2, the green one, probably same unit weight, it has some cohesion, lower friction angle. And material 3, same unit weight, higher cohesion, but lower friction angle. Same clay material. This time we do a grid search, no load, no groundwater, and we look at the results. That was it. So, ordinary method, a Swedish method, gives a factor of safety of 1.23 with a failure surface that's starting at pretty much at the toe and goes through some of the materials. Okay, so let's see what Bishop Simplified is. Bishop Simplified gives 1.4. The location of the failure surface is more or less the same. So if I ask you a question, which one do you trust more? Swedish method or Bishop Simplified?
In that case, they're very similar because there's no groundwater. Maybe it's Swedish method because the factor safety is slightly lower.
Think of what's included in the Bishop's method that's not included in the Swedish method.
Maybe it's Swedish homogeneous, fight for the zero. Soil is non-homogeneous. Soil should be homogeneous.
Okay, Swedish method. What's in the Swedish method? Okay, look at the slides. What's not included in the Swedish method that's included in Bishop's method? Yeah, she said, interslice forces. Swedish method said, I don't even consider it. Are there any interslice forces? Let's see. For fun's sake. Bishop Simplified. Actually, let me show you something interesting. Oh, no, I can't show it here. Some other methods. Jones's method. No. So I can actually get the line of truss. So these are the found locations of the application of the interslice forces. You see this line above there? That's the line of truss. That's, you can get it in other methods. Spencer, GL. So, going back to the original question, which one would you trust? I would probably go with Bishop Simplified because it has more complete understanding of. But let's look at the one that does everything. GLE Morgenstern price. So 1.37, GLE says 1.37, and a failure surface is more or less the same as the Bishop's, the more deeper seated one. So I would go with factor of safety around 1 point whatever, 3 something, 7, 8, 9, something like that. If I go back to ordinary one, 1.23, and somewhat shallower. So each and every case, each and every scenario has to be looked at in a context of what the method is used and what is. And let's look at one more of the limit equilibrium ones. I think it's this one. Yeah, this one. So this one, without saying anything else, comment where the failure surface is going to be. In order to help you a little bit, let me show the material properties. So soil 1, the yellowish one, has unit weight of whatever it is, cohesion, and friction angle. Soil number 2 has a unit weight of that, no cohesion, and friction angle of 10. Okay, so now you know what material is what. So let me ask you a question. Where would the failure surface be?
Define the material. The second material.
It's along the green.
Yeah, most of it will occur in this weak seam along the green line. So would we use Bishop Simplified, a Swedish method for this? No. Well, let's look at the results. So we have a non-circular failure surface. That's sort of expected. Okay, so let me look at the possibilities. Let's say Morgenstern price. It finds it that it's running along. I defined it that it is going to be, you see these 2 arrows and a red line. It says look for a component of the failure surface along this line. So it found it that it's coming out at the toe, it goes along the weak seam, and it's going up and breaking out. That has a factor of safety of 0.7. Okay? So from the definition of the problem, you as the person who's doing the analysis, you have to have a good understanding of what will work. And this is what the course is about. What method is appropriate? So now let's do something completely different. Let's turn to finite element slope stability analysis. Let's turn this off. So while this is loading up, think about it. What do you need for a finite element analysis to do slope stability? So it's the same 2-to-1 slope. What else we have here extra that's not on the sketch over there? Yeah, we have the finite element mesh. I'll not even get into that at all. So for finite element analysis, you again specify the boundary, the geometry, you specify the material. So soil 1, it is a more Coulomb material, tensile strength I can give, friction angle, cohesion. Based on the material model, I can have residual post-failure strength. I can change the material model to Drucker-Prager, Cam Clay, all sorts of stuff, softening, hardening models, and all of those of you who had a midterm last Friday can say that these are really fun things, right? So I have much more liberty of playing with what it is. So I have the geometry, I have the soil properties. Do I specify any method or any grid or anything else? Nope. I just press the button. And note that the computation, and intentionally I have the analysis run, it will take a little bit longer. Right now what it's doing is it's calculating. And keep in mind, look at this number. The strength reduction factor, SRF. Remember when I showed you how it's kind of having the interval, how it's finding, oh, it's already gone, how it's looking for the critical factor of safety by reducing the strength. It does not converge, it's losing the value halfway between what works and what doesn't, and so forth. And it got the results. So, let's see the results. So what is shown here is the maximum shear strain. Okay? But other thing is important here, that there are these various tabs. Each corresponds to a scenario of the shear strength reduction factor. Anything that's greater than 1 or around 1 or where it found it. So for this problem, the finite element analysis says that the factor of safety, or SRF, is 0.995. Why is it saying it? Remember I talked about it at the beginning of the class today. What is it basing on that the factor of safety is? Yeah, the maximum shear strain. That's what's being plotted up. And it's giving you, it's telling you this, and it's giving you a nice contour plot where it's, what's plotted up is the shear strain. So my question to you is, where's the failure surface in this? Oh, that's simple. Let's turn something on. Let's look at the actual displacement vectors. These are the arrows that are in a direction and their size is as the displacement that's occurring. Is this more helpful? Right, so we can say that the failure surface is kind of, judging from the size of the arrows, is kind of up here from the toe, somewhere in that direction. Another way to look at it would be, let's look at the various stats. When SRF is 0.99, there's not much different. 0.95, not much different. Let's go above when it's already failed. What do you see on this plot that you do not see on this plot? This is a case where my factor of safety was basically too high. This is where the material failed. What's the difference between the two? So there's a much more defined of this shear band here. This is where the basically shear failure occurs. So this is one step after the critical factor of safety. And this is, say, so this is at 1 and this is at 1.49. Like, you know, that already long failed. So we have a better understanding of what this is, what's happening here if the failure surface is not obvious, is to go one step above it. And then you would see that there is this shear band form. Now, we can have the option of looking at other things, such as displacement. Let's look at total displacement. This is the amount of material that's moving versus not moving. Blue is no movement, red is a lot of movement. So for an SRF of 0.99, not much happening. Let's look at an SRF of 0.995. You see that the blue is staying put, green is kind of moving, red is really moving. And if I go to the critical one, or one above it, sorry, it's more kind of tightening up, and if I go way past it, this is meaningless. So around the critical one and one above it, so anything that's the boundary of the blue and light blue and greenish, that's where your failure surface would be. Or I can look at, for example, stresses. Not sure we'll look at. Minor principal stress. This is not really telling you anything. Right? So you have to look at the right quantity. So let's look at another example of finite elements that we already looked at with the other method. Right? Same slope. We said that the failure surface is somewhere from the toe, and I think it was around 1.38 or something like that, we said, if I'm not mistaken. So let's see what finite elements are giving us. I'm going to let the analysis happen. I'm going to leave the cursor here. So you see how the strength reduction factor changes as every time it's reanalyzing it. And let's look at the results. Okay, so maximal shear strain is shown, and the SRFs go 1, 1.3, 1.33, 1.35, 1.36. It says that's the critical, 1.37, 1.45, 1.6. So the other method, I believe it gave 1.38 or something like that, 1.4 for GLE. So let's see what happens for SRF of 1. You see that there is some high shear strain at the toe, but not much, no failure surface. It's more increasing and something starting at the top at 1.3, 1.33. Not much change, 1.35. You see that these lobes are getting closer to each other. 1.36. See, it's kind of coming closer, and let me go above it. 1.37, which is the failed state, non-converged state. So these are the results. And it really shows this shear band. And if I turn on the arrows for the displacements, again, you see that most of it is confined to that region. And if I look at contours of displacement, turn off the arrows. So for 1, nothing happening. 1.3, it's not deemed to be critical yet, but you see how the mass, what mass of soil is moving, that's not blue as opposed to the mass of soil is not moving. So one above it kind of tightens down, and that really gives you an idea where the failure surface is. And if I go way past it, these are kind of meaningless. Now I can look at yield. So the X says mean shear failure of the soil, 0 means tensile failure of the soil. This is how the material behaves. So anybody's guess why there is so much tensile failure on the top, and what could that mean? Yeah, it's the soil is failing and it's dragging everything behind it. So if I would do this in the limit equilibrium method, it would be prudent to install a region of tensile cracks with reduced material strength. Because the soil is moving downwards. We show the arrows again. You see all this material is moving downwards, so it's dragging the soil behind it. The soil far away there is basically stationary. That causes tensile stresses here in the top end. That leads to tensile failure. Now, if you look at it in more detail, the X's are where there's shear failure within a soil. That kind of sort of follows the failure surface itself, but it does some other funny things that are not going to talk about. There are multiple ways to assess the situation and determine what failure is. So let me just go back to maximum shear strain. So you see that the band where the green is kind of at the boundary of where the X's are. And let's look at yet another model. So another embankment, and this time a sloped core, right? The orange one, sloped core. Let me turn this off. Sloped core, transition zones, rock shell, and another filter in between. Do I have to give this finite element method which way the slope is, left to right, right to left? Nope, I do not. Let's look at the results. It will find the critical one. So I'm going to keep it in a strength reduction factor, which is it's 1.9, find 175, 225. It's kind of bouncing around trying to find where the critical is. And other things that are interesting to watch is the convergence of the method. It has to be whatever number is here that's running there, it has to be less than this number for it to be called convergent. So that's, again, beyond what the course is about, just giving you an idea of what it does behind the scenes and when it says it's convergent as opposed to non-convergent. So the results are done. And maximum shear strain, we have a variety of SRFs from 1, 1.3, 1.6, 188 says to be the critical, 189, 19, 225. So you see that there is no water, so what state of the embankment then this is corresponding to? Yeah, end of construction. It's built, there is no reservoir loading, there is nothing. So they're making sure that the whole thing doesn't fail without being filled. So now you can kind of guess that there's going to be a failure surface somewhere in this direction, hinting from 188. So let's go to 1. You already see that there are some high shear strain developed here at the core and also at the transition or filter. 1.3, 1.6, 175, 182, 86, 88, and let's go one above. So there is, but what else is happening here? Can you comment on it? We've been watching the one here in the center, but something else is going on. Pardon? I take the word failure. So, remember, this will find all the potential problems. So even though the high or the first one where it stops is at 188, is going to be a failure that goes this way. There are localized failures at these benches with a factor of safety of, very close to what the main one is. So let's go beyond there. So you see that there are failures. And if I go really like this is nonsense, you'll see that there might be some other instabilities, but the material will fail much sooner. So let's look at 188 saying the critical. Let's look at the arrows. They're not really helpful. Let's look at the maximum displacement. So you see that the shell at the top of it and everything is kind of coming down, and you see that might be a reverse curvature failure based on the colors, that it kind of comes down, cuts through the core, turns in the transition, goes up and then down again. So the moral of this story is that you would be able to catch not only one, but perhaps multiple critical failures of the embankment dam, irrespective whether they fail from left to right or right to left. Right? There is one developed here of the bench. It's much more localized failure. And also there is another one for the next bench that's developed, other than the one through the core and kind of coming down. And let's look at one more just for fun's sake before quitting. So this was 4. So similar to one of the problems we look for the limit equilibrium one. Can anybody comment on it without me saying too much other than showing the material boundaries or the material properties, sorry. So soil one, the yellow is more Coulomb, tensile strength 28, so it has some tensile strength, some cohesion and some friction, and soil 2 has basically no cohesion and very low friction. So this green one running at the bottom of the model is a what? Yeah, it's a weak seam. So we kind of have a good suspicion of where the failure surface is going to be. So let's run the analysis. I've already ran it. So I'm looking for maximum shear strain. You see that the hot values are within a weak seam and SRF of 1.17. So let's just step from one side to the critical one, and you see that you don't see much. You have to go all the way up there for it to actually form a full failure surface. So this case, the 1.17 is not really showing you a developed band of shear failure. You see that it's somewhere up there. I would be even inclined to say that my model doesn't go far enough to the right because there is a lot of shear developing here at the boundary. So let's switch to another view. Solid displacement, total displacement, and look at 1.16. So now you can sort of see that most of it is most of it is kind of coming down, moving along, there's nothing happening underneath, and kind of exiting here at the top. If I step one step beyond, it kind of confirms it that that's where most of the displacement is. If I really go far enough, way past, you see that the movement is kind of in this region, that part of a circle, horizontal, and the other part of a circle coming this way. And if I turn on the arrows, you see that there's very little movement occurring in the blue, a lot of the movement here, nothing underneath, and coming out at the top. And if I look at now shear and tensile failure, again, I expect a lot of tensile failure at the top due to this dragging of the soil mass, shear failure within the material that's failing, definitely tensile failure, kind of ripping and dragging of this weak seam, and underneath it, as the soil is failing, and some of shear failure underneath, and that's pretty much it. And other fun thing, this is kind of the deformed surface, so you see how much of kind of slumping is going on as the slope fails. So, I hope this gave you a good cross-section of the potential problems that we can analyze. But like I say, the course is not about what the software can do. It's about your understanding and interpretation of the results and creation of the models of what goes in, what will work, what will not work, and so forth. So, any questions? Other than where the door is, and everybody runs off to, I guess, study for next week. So, no questions. Like today's lecture, there's not much that I would include it on a final, other than the material that I covered for the first half an hour. That is on it. Finite element, the slides, that's on it. But the demonstration of the software and everything is basically what I deem to be a practical application of the material. And I hope by looking at this, it put it into much more context of what you learn and what works, what doesn't work, what if it's giving you a bunch of results, which one is the one to take, and so forth. Okay? So next week, midterm 2, 1.5 hours, just like the previous one, obviously no lecture afterwards. And a week after that, we have 3 weeks of wonderful presentations. Practice, practice, practice. It's not easy to stand here and talk to the class. Okay? Hopefully nobody will faint or run away or anything like that. See you guys next week.